All right, let's talk about dehydration with the POCL3, the phosphorus oxychloride. So why we're using the POCL3 is to convert the OH into a good leaving group because, again, I'm going to keep repeating it, OH is a what? Bad leaving group. So the idea here is almost the same, except from like E1, we created a carbocation intermediate, but in E2, we do not, NOT. So please make sure that you follow through with the steps with me. Now, again, with most elimination mechanisms, we're always wanting to go for the Zatsef product, which is the most stable double bond intermediate. We can also get a minor product. So it just kind of depends on what the instructor wants, but most of them tend to ask you to provide the major product always. In this particular problem, I'm using a secondary alcohol, but I'm letting you know this will also work with primary and tertiary ones. The difference is you need to really make sure of what's on the line and being used, and then you'll know what type of mechanism you're doing. So for this one, we are going to start off by creating the OH to be a good leaving group. So this is going to attack the phosphorus group and kick off one of the CLs. When it does, the structure gets really big and really complicated quick. So we now have, I'm going to rotate that hydrogen that's connected to the alcohol group up. Then I know this is going to be connected to the phosphorus. The phosphorus has the carbonyl, and now it has two Cl groups. And remember, oxygen has 3 bonds now, so it gets a positive charge. And you still have the Cl minus, one of them that popped off. And this particular step is when you need to know what the pyridine looks like. Now, pyridine is a heterocyclic aromatic compound, which means it looks like an aromatic or a benzene ring. Hetero means there's a electronegative atom embedded into the ring, so that's nitrogen. I'll put the nitrogen in a different color just so you can see it. So it could be a little bit more prominent. There you go. And that now, this pyridine is going to grab the hydrogen that's positively charged in order to neutralize it. So when we make something into a good leaving group, we don't want it to be unstable in most of the cases. And later on, as we go and do different mechanisms, you'll start to recognize this exact same pattern. So there's your oxygen, the same group. And now your pyridine, you still have the Cl minus, that's just lingering right now. You have the pyridine that just grabbed the hydrogen. And nitrogen is not supposed to have 4 bonds, it should only have 3. So because it has 4 bonds, it gets a positive charge. Now that you've created the good leaving group, we can now use the Cl to create a double bond. Now, how do we know which way we want to create the double bond? So at this step is when I'm going to rewrite this picture one more time on the bottom so you could see the 2 different answer choices. So this is when we actually use the Cl to do the E2 elimination, which is a concerted mechanism. So remember that Cl minus is negative. And now how do we know where the Cl minus is going to attack? Wherever the bond of the oxygen is, wherever it's connected to, you're looking at the neighboring carbon. So that would always be these 2 right here. This one's secondary and the one on the bottom is tertiary. Obviously, the one on the bottom is more stable being tertiary, so we have to deal with the hydrogen on the tertiary group. So I'm just going to mark this one as tertiary, and we'll deal with the hydrogen up here, which happens to be secondary for this case. So I'm just going to put this one secondary, this, oops, big 0. It's not a 30, it's a tertiary. And then we're going to do the elimination. So in this case, it would grab the hydrogen, make the double bond. Now when it makes the double bond, that's when this portion is kicked out. So when this is kicked out, and this one's a little bit more prominent. I don't think most of your instructors show you the byproduct, so double check to see your notes. They tend to just kind of want the quick way to get there. So again, grabs the hydrogen, makes the double bond where the bond of the carbon oxygen would be, and this just completely eliminates itself. So we will have the answer choice here, which is the minor product, and then we have the one here, which would be the major product. And again, it's because it's more substituted, which means when we look at the double bond, this double bond is connected to 1, 2, 3 groups. This double bond is only connected to 2. So this one's di-substituted versus the one on the bottom is tri-substituted. So that's the difference when it comes to the type of mechanism, and making sure that when you're looking for that hydrogen, it's always where the CO bond is. You look at the neighboring carbons to determine which hydrogen is more stable, so you can go ahead and get the right answer. Now, what if it looks a little bit different? So, just to give you another example. Now, if it's with stereochemistry or without on a cyclohexane ring, specifically cyclohexane. I'm doing this on purpose because there it is, trick question. If it's flat, no wedges, no dashes, you can clearly just mark the tertiary versus the secondary, and you would know that your final answer in this case would be this picture. Absolutely. Because we want to make the double bond to the more stable side, and of course the OH still can't be there because it's an elimination. So that's our E2. However, when it's like this, if you ever see a problem that's a cyclohexane ring with stereochemistry, you have to go through and do a chair confirmation. You really have no choice. Now, I would go back and review to see if your instructor had shown this to you. Maybe not. So I know you're yelling on the inside. Trust me, I didn't want to do this now to you, but it's best that I do this now. So the mechanism exactly the same, but the rule for chair confirmations is that the OH, so you're supposed to be removing water. No matter what, you're removing water in the mechanism. When you remove water, you want to make sure that the OH group is in the acyl position, and so is that hydrogen. So hydrogen plus OH group, it has to be in the acyl position in order to be properly eliminated. So even though this is tertiary and this is secondary, never, ever, ever assume that the double bond will go tertiary in this case due to stereochemistry. So first, I like to save time, so I don't like to redraw chairs like the ring flip of the structure. So I tend to look at my OH group, that's my first step, and I determine if it's going up or down. In this case, it's going up, and the isopropyl is going down. That's my step 1. I know I need my OH group in the acyl position, so the goal is I'm going to look at every corner that's automatically pointed up, which is this one here, and this one. Those are the 3, so here, here, and here, that are pointed going upwards. Now, any one of those corners, you're allowed to just immediately draw the OH going up, and it's immediately acyl. It's the coolest thing. Then that means if you make your OH number 1, which you should in naming purposes, then number 2. Now, if you want to go number clockwise or counterclockwise, that's up to you. Now, I see that number 2, I'm making my number 2 here on the bottom. I see that my isopropyl is going downwards, which is also in the acyl position. But I need a hydrogen in the acyl position. So does this number 2 have an acyl hydrogen? The answer is no. However, the other carbon next to the OH, which is this one, I'm going to draw it really lightly. It's going to be, let me erase that to make it a little bit better. You'll see that there's a hydrogen in the acyl position on number 6. So if I counted all the way through, this is 3, 4, 5, 6. The numbers in orange are the numbers of the ring. The numbers in pink were just the classification of the carbons. So really my acyl hydrogen is on number 6. So when I would have to do the elimination for this problem, I would expect my double bond not to go towards the side that has the isopropyl, but away from it, which is also equal to me not touching my isopropyl group and placing my double bond to the less hindered side. So you see, in this particular case, because of the stereochemistry of the cyclic ring here, we had to think of the chair conformation. If there is no stereochemistry, then you can completely go towards the more stable and create the Zaitsev product. But in this case, we created the minor product happens also to be the major product, because there's no way, absolutely none, that there could have been a double bond going in between this way, all because the isopropyl group is in the way of creating a double bond going this way. So review this concept, but really kind of gauge it towards your notes and what your instructor had taught you, so that way you know when to deal with it. But you can't say that Kess didn't show you how to do this.